Greetings all. The earth is the Lord's and the fullness thereof. This topic about the earth and its magnetic field I find very, very interesting and fascinating. And I hope you do too. I wish we had an earth science class. I wish we could all spend a couple of weeks just talking about the incredible design of the earth that has uncountable number of aspects to it that make it exactly right for there not just to be life, but to be intelligent life that's even investigating these kinds of things. There's lots that we don't know here, which I'll comment on as we get going. As we mentioned a couple of weeks ago, the first thing that takes you by surprise is that the geographic north pole of the Earth corresponds to the magnetic south pole, and the geographic south pole of the Earth corresponds to the magnetic north pole. And that is why your compass, if you're holding it in your hand, points towards the north, because the north geographic pole is the magnetic south pole, and the north pole of your magnet in your compass is attracted to the opposite pole at the top of the Earth there. Another thing that's kind of interesting is that the geographic pole and the magnetic pole are not exactly at the same spot. There's a little bit of an angle of about 11 degrees or so, difference between the two. That means if you followed your compass straight north in order to find Santa Claus and ask him for a cure for a virus or some such thing, you would actually be 1,300 miles away. He would be at the geographical North Pole, whereas you would be at the magnetic North Pole. That vocabulary word, the dip angle, right here, that is a vertical angle, because as you go from the equator, where your angle will be 0 degrees and your compass needle will be perfectly horizontal, by the time you get to the North Pole, it's going to be pointing straight down. Moving on to the next page. The difference between the geographic pole and the magnetic pole is called the magnetic declination, and you can see it varies across the surface of the Earth. If you look at the picture of North America, primarily on the right side of the page. And a lot of that has to do with things like iron ore deposits in the crust and elevations and things like that. Another thing that we would like to know is, so why does the Earth have a magnetic field in the first place? One of the principles in this chapter is that anytime you have a moving magnetic material like iron, which would mean it would have to be a liquid, moving charges create a magnetic field. And therefore, based upon that idea, but also seismographic information from all over the Earth, we have learned that the very inner core of the Earth is solid. There's an outer core of the Earth that is liquid, and that's where we think the iron is generating the magnetic field of the Earth. Around that liquid outer core is the mantle, and then the thinnest of thinnest membranes on the surface of the mantle is the actual crust of the Earth. And we have never, ever gotten deeper than the crust. We've dug some pretty deep holes. Russia finally gave up after, 5 or 7 kilometers a number of decades ago. We've never gotten below the crust of the Earth to see what the mantle is and take a sample of it. Another thing that's kind of interesting is that the Earth's magnetic field evidently has reversed itself every few million years. And the reason we know this is because if you, for example, go to the center of the Atlantic Ocean, going from north to south, and bisect the ocean, and of course you'd be zigzagging back and forth a little bit, you would find that new crust is being formed as a result of material from the mantle coming up through the crust and pushing aside in either direction, east and west, creating new mantle. And As a result, it brings with it some of this iron material, and when it cools, some of the magnetite or iron ore is locked into its magnetic position. And so we can take samples on either side of that midsection going east and west. And the farther away we get from the midsection, eventually we find that the magnetite crystals are directed in the opposite direction. And we've had several of these magnetic field reversals over the year. And there's some evidence that we might be headed for a new one, but I don't think it's anything you need to worry about. We have no idea what causes this. So if any of you want to go into earth science or geophysics, that would be very fascinating to discover that. Another thing that's kind of interesting, of course, is that animals have some rather remarkable features in order to detect these magnetic fields. Birds seem to be able to use it when they go on their migrations. Butterflies use it. For example, maybe you remember me giving a talk on the monarch butterfly about 5 or 6 years ago in chapel, and they navigate to a location in central Mexico, an hour or two just west of Mexico City up in the mountains. Their population has been greatly depleted this year, tragically. We hope they make a comeback this coming year, but somehow they managed to navigate from all over, from west of the Rockies to the Atlantic Ocean, and all end up down in the same location in a few square miles of forested land where they overwinter. And one of the reasons they do this is through magnetic sensing of fluctuations in the Earth's magnetic field. We also have bacteria that seem to have the ability to sense magnetic fields as well. There are various organisms that can respond to light as well as to gravity, and then in this case to a magnetic field. The last sentence in that paragraph, by the way, says NASA scientists believe it may be fossil of ancient martial bacterial life. Did you read that? And that has been rejected a long time ago. Now we get a little bit into the math. And the main principle here is that when a charged particle enters a magnetic field, it will be deflected. When a charged particle, positive or negative, big one or small one, proton or electron, when it enters a magnetic field, it gets deflected, which means there must be a force acting on it. And the magnitude of that force that causes the path of the charged particle to change depends, as you might expect, on the size of the charge and on the strength of the magnetic field, as well as the velocity of the charged particle moving through that magnetic field. And you put all of that together, and you get equation 19.1. And then, of course, if you enter that magnetic field not perpendicular to the flux lines, but at an angle, you don't experience quite as much force. And that's why you have the sine theta in the equation. You can solve this equation for B, which is the strength of the magnetic field, and that way you can use the easier information to obtain, the force of the deflection, the charge of the particle, the velocity of the particle, and the angle of interaction to actually calculate the strength of the magnetic field. We would measure that magnetic field in something called the Tesla, or more often we might measure it in terms of the Gauss, which is not an MKS unit, but a CGS unit. Roughly there are about 10,000 Gauss in 1 Tesla. And a Tesla is sometimes called a Weber per meter squared, where a Weber is a measure of the flux lines, and per meter squared then gives you the flux density, Webers per meter squared. One of the interesting things about a charged particle entering a magnetic field and getting deflected is now you're forced to work in 3 dimensions instead of 2. And so when we try to predict the direction that the charged particle is going to be deflected, up, down, left, right, in, or out of the page, we need to use what is called the right-hand rule number 1, which implies, of course, that you're going to get several other right-hand rules in this chapter and the next chapter. Now, first of all, we have to remember that the right-hand rule is the rule that you use for positively charged particles entering a magnetic field. If you have a negatively charged particle, then you would use your left hand. And that's not an uncommon thing for an AP test to do, or for some AP test teacher to do. And that is to talk about an electron entering a magnetic field instead of a proton. Now, in the book, they have you use your thumb to indicate the direction of the force that the charged particle will be subjected to. They have your fingers, when they're pointed straight away, as the velocity of the charged particle as it enters the magnetic field, and then the curvature of your fingers representing the flux lines going by convention from north to south. I don't like that rule. I like to use a rule where my hand is flat. And when I have my hand flat, with my thumb pointing up and my 4 fingers straight forward and the palm of my hand coming into my face, I use the palm of the hand as the force. I use the fingers representing the flux lines, and I use the thumb as the velocity of the charged particle. And using the fingers as the flux lines and the palm of your hand like it's pushing the charged particle makes more sense to me. You get the same result. Now, in example 19.2, we have an opportunity for you to use your right hand, because here we have a proton, which means use the right hand. We have its velocity at 8 million meters per second, and it's going to be entering a magnetic field. So if you were to take your right hand, and using my technique, you can always use the book's technique on your own. If you put your fingers in the direction of the green line, which would be coming towards you, and your thumb, and your hand now is in a pretty awkward position, but your thumb pointing in the direction of the red line, meaning velocity of the proton, you'll find that the palm is pointing straight up the page, pushing the charged particle upward, which means that as that charged particle is following the red line, it's actually going to begin to curve upward and go towards the top of the page. I should also mention then that when you are answering test questions and homework questions, and you are using the right-handed rule, not only will you need to find the magnitude of the velocity or the magnetic field or the force, depending on what you're solving for, but you're going to have to use or indicate the direction. And make sure that when you indicate direction, you don't say something like top or bottom. You want to say into the page, out of the page, to the top of the page, to the bottom of the page, to the left of the page, or to the right of the page when you're looking at a picture. Here is another example, and this time you have a charged particle that is trapped in a magnetic field, if you're looking at figure 19.9, and what you'll notice are a bunch of green X's. Those green X's, and we're using green in this book to represent magnetic field lines or magnetic flux lines, those green X's are meant to look like the back end of an arrow. So if an arrow with its feathers were pointing straight into the page, what you would see looking at the page would be the tail end of the arrow, the feathers crossed. If this was an arrow coming out of the page towards you, we would represent that with a dot. So in figure 19.9, the magnetic field is going into the page. It's going from the north above the page towards the south in the page. So if you're using the right-hand rule that I like to use, I would be pointing my fingers into the page. In fact, I might even actually touch the page of my book or my iPad, and my fingers would be touching it, my palm and my hand would be coming straight up at me. Then the next thing I would do is I would have my thumb going in the direction of the red line. So pick your proton. I'm using the one at the bottom of the circle. And so my thumb is pointing to my right. And you can see my palm is in the direction of the blue arrow, which means there will be a force pushing my charged particle up, which would mean it would be traveling in a counterclockwise direction around the midpoint of that diagram. Did you get that? Now, if my charged particle is traveling in a circular path, that means it's experiencing a centripetal force. And this centripetal force, mv squared over r, is equal to the force that's acting on the charged particle, the proton in this case. And so we can set QVB equal to mv squared over r. When you solve this equation for r, you get equation 19.5. And this allows you, for example, to determine the radius of the curvature of the path of the positively charged particle in a magnetic field whose flux lines are going into the page as it begins to travel in the counterclockwise direction. This has practical application, for example, in that we can accelerate particles in huge, massive devices called cyclotrons, that sometimes the path of our charged particle could actually be many meters to many kilometers in length. If you look at the bottom right of the page, if this charged particle, instead of just going around and around, is given a little bit of an oomph forward, you will get this cyclical pattern, a helical pattern, as it travels in a corkscrew kind of passage from left to right as it comes out of the page towards the right. And you can speed charged particles up faster and faster. And of course, the ultimate goal with a cyclotron or even a linear accelerator is to smash it into a bigger particle to see what pieces the bigger particle might be made out of, or to try to get the smaller particle to stick to the bigger particle and create an even bigger one. That's one of the ways you can make new elements that do not naturally exist. And of course, on the next page, we have everybody's favorite analytical device, the mass spectrometer. So this, for me, is a BII moment, a back in Idaho moment. Because the mass spectrometer, what we always were doing was shooting a beam of charged particles at a target, and when the beam of particles struck the target, it would dislodge whatever molecules might be on the surface of that target, like residues of chemical weapons, and they would fall apart into pieces and be captured in an electromagnetic field, and then you would be able to count them. If you turn to the next page, 629, you'll see the mass spectrometer. There are different types, but this particular one allows you to separate two isotopes from each other. Isotopes would have the same number of protons, but a different number of neutrons, so they would have a slightly different mass, which means when they're entering that little slit by the letter S on the right side of the picture, they are from the bottom of the page. They enter where those green X's are, so you have a magnetic field going into the page. And as these different isotopes enter the field, the one with the smaller mass is going to be bent at a tighter curve than the larger mass can be bent. And of course, if you take your fingers and point them directly into the page, representing the Earth's magnetic field. Your thumb at point S is going upward because that's the direction that the isotope particles are entering the magnetic field. You can see the palm of your hand is towards the left, which means it's going to push or deflect the particles towards the left as they continue to travel in the magnetic field of the mass spectrometer. We're going to stop right there for the time being.